Awesome data mining, welcome.
I really appreciate it. And also, Marisa Moyoso is here from Scala as well. So she'll help with questions and help put this deck together. So as Seamus said, we, CBOS Technologies, we are working on planetary scale agricultural simulation optimization. So we are trying to simulate sort of hundreds of variables of the agriculture system every day at subfield resolution in multiple countries and multiple crops. Those models, like I said, have thousands of variables. And the data that we ingest actually has millions of data points per field, and obviously, hundreds of millions of fields. And that's actually a rich domain model, so we're not like a black box machine learning company. We're really based in agricultural science, plant science, soil science, crop science. So we have this rich domain model with hundreds of interactions, because it really is a system, and hundreds of outputs. And we don't believe in silos at CBOS, so we like to think the way that we work is to really shred the silos of these disciplines, which is sort of very different from some like that. So we have this mixed team of software engineers, data scientists, remote sensing and GIS, and then the actual domain science. That's this plant soil science chiefly. And the way that manifests is that we're developing new approaches that fuse typed functional programming with data science. And that's something that we believe in very strongly and are really passionate about. So some of our internal tooling today, for instance, we have a combinator library that actually generates Markov chain Monte Carlo models. So we use sort of functional programming concepts and types and lenses and prisms and other optically things to generate from a very succinct specification, like here on your left, to generate these really complex models and then run them. And we're also extending that to making higher order functions for computer vision and for GIS and spatiotemporal models with monads and right? So, and stop me as I go along if you have any questions. I'm happy to answer them. So at CBO, we also believe in this high-powered fusion of Bayesian data science. Like I said, with this mechanistic modeling with machine learning, and you'll sort of come to know more about what we think machine learning is later. That's usually in this process of taking the theory of the literature, making these scientific mechanistic models, doing the statistics to really say, is this really valid? Does this really work? Which parts are most important? So that we come up with some synthesis that we can then use Markov, Monte Carlo, and Bayesian methods to define these nice peaky posteriors in these large spaces of uncertainty. This is obviously projected down a couple dimensions from hundreds of dimensions. And just a little bit about us. As Seamus said, so Marisa actually was at Tufts for math, went to Boston University for more math, and worked at a variety of places as a software engineer and as a data scientist doing numerical weather prediction and remote sensing, and is now one of the data scientists at CBOS. And I actually came up through genomics and started a DNA sequencing company before doing data mining at Monsanto, and now I'm software and data science at CBOS. And we sort of wanted to put this story to our programming languages evolution over time. So CBOS is a Scala shop, actually now, and that's something that's important to us. And sort of interesting in the data science space, as we'll talk about today. Why are we giving this talk? What did we talk about? Well, like 2 months ago, we showed up at CIC for this meeting and no one was there because the speaker canceled like the day before and we didn't bother to check our email. And they were going to give us a talk on nonparametric Bayesian cluster analysis. And we were sad pandas about that, right? And so we decided, well, we can do that. We can give a talk about this because it's something we're really excited about. I mean, we're not going to do it in R, we're going to do it in Scala, which is more exciting to me. So that's this. Some background. We're going to kind of blaze through some of this stuff today and talk first about the mathematical and sort of statistical elements. And then we're going to talk about the computer science, software engineering elements of making this work. So fusion, of course. But if you want more background in detail, read this paper, this Indian buffet process paper from Griffiths. It's spectacular. If you look try to find the best paper on Chinese restaurant process stuff, these slides from Mark Johnson are totally the best. Anything you can ever possibly find. And there's a great review article, this Gershman and Bly, on Bayesian nonparametrics. If you're not familiar, Bayesian nonparametrics. Great papers. So there's actually a whole world of these Dirichlet process mixture models, and we can talk about that for a long time, and all the derivatives. But today, we're just going to focus on the Chinese restaurant process, which is sort of one subclass of DPMMs. And even more specifically, we're just going to talk about count data. You could make Dirichlet process mixture model in lots of forms and ways, and it's actually sort of a model that has another model nested in it. And we're just specifically picking count data for today to make things simpler. All right, so what is DPMM? What is CRP? So I'd like to start with a puzzle, like a problem that we could possibly solve. So let's say that we have M&Ms. And there's different kinds of M&Ms, right? Like maybe 348 days of the year, you can buy regular chocolate M&Ms, and they have some distribution of colors. And for 14 days out of the year, you can buy Christmas M&Ms. And obviously they look different, right? Highly biased towards red and green. And maybe for a weekend, a long weekend out of the year, you could buy 4th of July M&Ms, which is really a thing. So they're like red, blue, and white. And there's obviously overlap between these colors. And also, I don't really assume that the manufacturing process is so perfect that you can't get bleed over colors between types of bags. Gotta account for that. So let's say I take a bunch of these bags, and I put them in a hat, and I erase all the labels, and I give you back out the unlabeled bags. And you only get to take out a handful of M&Ms from each bag. So that's all the data you have. The labels, handful of M&Ms from each of 365 bags. The problem is for you to tell me how many kinds of bags there are. So you don't know anything before the hat, right? How many kinds of bags there are? That says how many kinds of bags there are again. That's wrong. How many kinds of bags there are, which bags are which, and what the model of each bag is. Basically from nothing. It's observations. That's the kind of problem that DPMM will solve.
Sorry, how can you do that from just getting the M&Ms out of one bag?
You get a handful from each bag.
Oh, you do?
But you don't know
okay.
the labels of any of the bags. They're grayed out here.
Okay.
So just to ground this, again, obviously this is from scikit-learn, which is a Python thing. Data science, big field, right? Specifically, we're talking about, and you can kind of break that down. I like how to break it down into classification, regression, clustering, and dimensionality reduction, right? Major fields of data science. We're going to go down this clustering tree, and I think this sort of sets it up well in a little flowchart. So assuming we have labeled data, no, you don't have labels on the bags. Do we know the categories? No. The number of categories, we have no idea what that is. I didn't tell you you get 3. Maybe there's Halloween M&Ms in there, right? So we're definitely in this clustering spot. But when we were doing this at Monsanto, in my group, we actually want to do this on hundreds of thousands or tens of millions of bags, right? Not 10,000. So if you follow this scikit-learn chart, it says, number of categories, no, nope. Do you have less than 10,000 samples? No, we have a crap load of samples, right? So it ends in this tough luck bubble, which, we're engineers, right? So you can ask some people the data science, what do you do? And you get answers like this, subset your data, and then it'll be smaller, and you can use the method that's in there, right? Or use an approximation, use some variational thing, or some other method that's not fully Bayesian. And there are some more sophisticated things you can do. There's this interesting paper in May 2007 from the NLP community, which tries to do this more efficiently. But we're engineers, and we do not have to make trade-offs. So the point of this high performance implementation is how can we still use this high-powered Bayesian method without making trade-offs? And so that's the story. So first, you might want to know, why are we just using a method that's not Bayesian? Like, why don't we just use Kmeans, right? Well, first of all, we don't know what K is. So you could scan over Ks and try to make some way to decide which one you think fits best, right? But really, if you think about it at a meta level, I like to decompose a clustering problem into these four sort of desired elements that you like to have. So we need to learn cluster count. The way we do that in Kmeans is in an ad hoc way. It's like ad hoc, you specify K. We also need to have a measure of membership of any element into the cluster that it's supposed to go in, right? And Kmeans, that's also ad hoc. It's this like Euclidean distance. Like maybe you can transform your space and try to like pretend to yourself that that's meaningful in some way. But it's an ad hoc measure. And obviously you can do this in a more sophisticated way, but the sort of standard EM style iterations of Kmeans are not guaranteed for you to converge like the global optimum, right? This is kind of like a greedy method. That's not necessarily going to get you the right answer. So you can do something more sophisticated. But if you're doing like stochastic gradient descent, you may as well be using a Bayesian method. So I exclude that from reasons you want to use Kmeans. And at the end, you don't really have a great confidence measure of how well everything belongs to your cluster, how well you think your clustering is in totality. So that's kind of not what we want, right? So the advantage, really what we do in DPMN is make all of these things probabilistic. So for cluster count, we're going to have a probabilistic model of how many clusters there are. For the measure of membership, we're going to have a probabilistic model of what the content of every cluster is. We're going to use this sort of global optimizing method, Markov chain Monte Carlo, to solve this model back out, which in the limit of time is guaranteed to give us the global optimum, right? And we have a number of confidence measures. We have probabilistic measures for sort of every aspect of the performance of the system, which is great. And how many people are familiar with Bayesian methods? I can go through these more quickly, but Bayesian methods fundamentally are what we call generative. I think it's useful to sort of have a grounding of what it means to be a generative model. And this is my favorite example because it's outside of what we usually think of. Let's say that you take pictures of plants, and you want to know what the surface is, those are good ones, yeah. Things that you want to, and you want to know what the surface area of a leaf on that plant is. Like a generative model of that is a series of steps that create that data that you observed. It's kind of backwards. So we're not like discriminatively analyzing data, we're actually trying to generate a parallel universe with data that looks like the data we observed. And that's by some generative process and a series of dials that are like the parameters at every step that lead to this generation. So say in this case, I propose a 3D architecture of a plant, and then I propose a leaf that is somewhere on that plant. And actually, that setting on that dial, that's the answer, way back at the beginning. We're not discriminatively solved out at the end. It's actually the beginning. The setting on this dial, 32 square centimeters, is how big this leaf is. And then I propose a deformation of the leaf. I propose a coloration of the appearance. I propose some like 3D transformation matrix by which that 3D model is projected onto a 2D picture that I took. So generative models are composites of parameterized data creation process. And all Bayesian models are like this, even if you don't think about it. So let's do a generative model for clusters. Fundamentally, the way we do clustering in Bayesian methods is what we call a mixture model. And so a really simple one kind of goes like this. Let's say we flip a coin, and if it's heads, we're going to draw a height of a person, of a woman, actually, from the distribution of heights of women. That's the thing. So they're normally distributed with some mu and some sigma, and we're going to draw one. That's the x. The z is like this label, so the label of this one's a woman. We're going to put it on our list of people that we've drawn, right? Same thing for your tails. We're going to draw from a different distribution, from the normal distribution parameterized by the parameters for the n, and record that. And then we erase all the labels, right? And that's what you get back. So that's the mixture part. Like we have this generative process, creates a mixture of outcomes, and the assignment, these z's, are sort of unknown to you, and it's your job to recover. Does that make sense? So it's a generative process that generates a mixture by having multiple paths to get to the end. So now I can tell you the story of the Chinese restaurant process. And there's like this, in Bayesian nonparametrics, a tradition of colorful culinary metaphors for all the generative processes. I don't know. So it goes like this. You walk into a very large Chinese restaurant, which has an seemingly infinite number of tables, right? And the tables are really big round tables with a seemingly infinite number of seats people can sit around. So every diner walks in, and with a probability proportional to how popular each table already is, they sit there, right? And they can go around all the tables and decide where they can sit. And with some probability, they nucleate a new table that no one has ever sat at before. That's kind of the important part. And there's an infinite number, so we can do that for forever. And this is a family-style Chinese restaurant, so every person that sits at the same table eats from the same dish. And that dish is another probability distribution. And the data that you observe are like bites of the dish. It's a very extended metaphor. And that's how the data gets generated. The bytes are the data that you get to observe. So in our case, bytes are M&Ms, right? Tables are types of bags. People sitting at the table are individual bags of that type. And that's sort of the whole metaphor. So Dinosaur Diamonds, tables are clusters, and dishes are these cluster models. And like I said, the models, the dish that people eat, can be a mixture of Gaussians. It can be lots of different things. But today we're just going to focus on count data. Okay. So now we have almost all the pieces to be able to implement this generative model, mixture model, except for the model of type colors. And if you've done NLP stuff or Bayesian combined stuff before, you're probably like, oh, I already know the answer. But we'll just talk about it anyway. Is we're going to use a Dirichlet Compound multinomial model, which is sort of the standard Bayesian model for count data. And it sounds fancy, but it's actually super simple. The Dirichlet distribution is like multivariate beta. So if you ever seen a beta, it's got two parameters. It can be like pump or, sort of fluxes like this. You can sort of scoop the hump on either side. That's if I pulled, I don't have any coins. If I pulled a quarter out of my pocket that I might have bought off the internet and it's loaded, and you wanted to describe your prior state of belief over how loaded that coin is, you would use a beta distribution. From the beta, I would sample a number between 0 and 1, so 0 and 1. And that's what you then shove into a binomial to get the flips back out. Dirichlet is just that same thing, but in multiple dimensions. And with the added complexity that they have to sum to 1, right? So you get vector probabilities of dimension whatever, and all of those have to sum to 1. That's why in this three-dimensional case, it's on like a triangular simplex, right? So, and then that's its PDF, which I just stole from Wikipedia, and I have no idea what it is. I'll look it up on Wikipedia, it doesn't know how to use it. It's fine. Okay, so we draw from a Dirichlet is sort of prior probability on a vector of weights, right? And we use that to parameterize a multinomial distribution, which is just like multivariate binomial, right? Where if I have a loaded die with many sides and faces, what's the probability I land on any of those sides? And from that I can draw data. So in our case, the multinomial is kind of, you can think of it as a bar chart of weights across the colors, this vocabulary of colors that we have. And we can use that, in this case, to generate some very odd looking M&Ms that too much black. The one thing to note is that there's a simplification here. Dirichlet is conjugate to a multinomial. So you know, in Bayesian stats, we start with the prior, and then we accumulate evidence. With this likelihood, this multinomial, we generate this posterior. Well, in some cases, that turns back into the same form of distribution, and you can analytically do that through the simplification. So, Dirichlet Compound multinomial has one of these analytic simplifications. Questions? Sir?
Just wondering, the lower right equation, the index subscript k, in part of it is outside of the product term. It says k equal 1 to k, but the index k is also to the left of the pi.
Yeah, these sums are, it's not written here, there's some overall k. I sold this also from Wikipedia. Yeah, so that's subscript k. Oh, there was a, yeah, we'll go back to that. There was a note earlier which says, where? Non-whimsical figures are likely stolen. Just doesn't look silly, then I didn't like it. Okay, so everyone loves plate diagrams, right? I don't know how these they actually are. But since this model is a little complicated and like there are all these parameters, I think at least this labeled version is maybe good. So these are all the parameters in our CRP picture model. There's two priors. So there's a Dirichlet prior over essentially the number of counts, the number of types of bags. And in Mark Johnson's stuff, that's beta. Note that in a bunch of other stuff, people swap alpha and beta. So one of them is the prior on essentially the number of types of bags, beta here, and one of them is a prior across the color frequency. So that's the Dirichlet to our multinomial. So in the vocabulary of all colors, if you have some new type of bag, before you observe any colors at all, what's the background frequency of colors, or what's the error rate of the machine that puts certain colors in certain kinds of bags. Okay, then that creates this phi parameter, which is Dirichlet over beta, which is essentially how popular every table is. In CRP, you basically end up with exponential weights, so this rich get richer effect on tables. So if you think about, here there's like L on subscripts, but those could be up to infinity. We're just tracking the number of tables you actually have. This is kind of like a weight vector over how popular every table is. Phi. Z is the same as our men, women, height thing. It's just this label of like which bag is Christmas and which bag is 4th of July. So A is this essentially smoothing variable over the colors, the color vocabulary. So replicated for every type of bag, count of bag types, that's this L. So replicated plates are replicates, right? We have our own vector, this own beta vector. So that's, Christmas M&Ms are high red and high green, and 4th of July M&Ms are high red, high blue, high white. Those are the betas. So all that goes down here into the X's, which the X's are actually single sampled M&Ms. There are D such M&Ms for every handful, and you get a handful from each of the N. So that's kind of the model. That's all the parameters, and that's how the information flows between them and their distributions. So, what is beta in this case? It's not a weight. It's not like Kmeans K picking the number of clusters. What it actually establishes is a probabilistic exchange rate, a monetary exchange rate in units between having more clusters and having tighter clusters. So by setting this, you sort of change the trade-off of, if you have a cluster that doesn't fit really well, when is it going to decide to split that cluster into two versus, maybe it is a giant cluster, maybe it's more giant than it ought to be, but it's really coherent. It's going to keep it anyway. And that's what's really different than Kmeans, is that it's explicitly modeling these trade-offs. Okay, so there's also this sort of standard trick, which is we can analytically integrate out, like use calculus to integrate out some of these parameters, so that you don't have to worry about all of them. And specifically, we can integrate out estimating and worrying about those multinomial distributions, those thetas. And we get this much simpler formula that looks like this. So this is the posterior probability of the bag I belongs to cluster K, given everyone else's assignments. That's this Z negative I thing, and the two priors. And that's just this big expression, which is basically related to the number of members in each of the clusters. Because we should have this like exponential number of members in each cluster and some number of them. And it's more likely the more it conforms to that. And then we're basically just, this giant thing with the C's, just tallying up the C expression. If we add a given bag to the cluster, and if we don't add that bag to the cluster, it might be kind of hard to see that, but it's literally just the counts of all the colors of every bag that's at this, in this cluster at this table, with and without a given bag. And so really, it really reduces down to this C function, this product of gamma of sums. And just remember that this K, like you can always include this one extra new empty table too. Okay, so say we have this model. Like we have the story, we have the math, it implements the story. Now we need like a solver to fix this. And so, just in case you're not familiar with Markov chain Monte Carlo, it's a method to solve this. And it basically says, we have this model, we can use it to generate data. We can compare that data to the actual data we have. In this case, like not like quite so right. And it's a structured sort of algorithmic way to tweak all those dials until we get back to a generative process that makes data that looks like the observed data. And it's called Markov chain Monte Carlo for a couple of reasons. I think of it, it's like a numerical game of Marco Polo, and people aren't like blue, so like analogy ends there, right? It's a chain because you start somewhere and you're making challenges to the environment by evaluating your function, and you're sort of moving in the direction of higher probability. And it's called Markov because you can't teleport around the pool. Like you're in somewhere in the pool and you have to like make steps. And if you question,
No teleporting.
no teleporting. That's Markov. And if you were to tally up every place that you were, all the number of times you were at any place in the pool, that would actually recreate the target probability distribution of where everybody is. So we have this complex function that we can't solve analytically, but we can take samples of it in a structured way so that we can sort of converge on a histogram of samples, reconstruct that distribution. So one quick note on those priors. So we made some, Marisa helped us make some test data, just like random test data of M&Ms in those three classes. And then we ran CRP on it with sort of reasonable priors. It turns out we get 4 clusters. That top one is clearly 4th of July, and the second one is Christmas. And then, interestingly, like our normal M&Ms get split into 2 categories. And they actually have pretty different looking histograms. So it's probably an artifact of the way we generated the right data, because those actually look pretty different, which is interesting. Maybe we have crappy right number generation. But if you crank up alpha, like we just changed alpha to 50, that changes this trade-off, right? Interestingly, we don't get like 1,000 clusters because that cluster coherency still really matters. So we get like 8. So you can sort of see there's a titration of like Christmas M&Ms that have like increasingly more red, and those get split out. And something different happens if you crank up B to 1,000. That's sort of equivalent to adding 1,000 pseudo counts to all of the multinomial distributions for all the colors on all bags. And so you get a like compression of the number of clusters. So beta has nothing to do with the number of clusters, but because it makes them all look more similar, there's no reason to tell them apart, and they get traded off probabilistically to be combined.
which is pretty cool.
That's exactly what we want. Questions?
Can you talk a little bit more about how in the Monte Carlo you find these parameters, or more of the details of, I mean, Monte Carlo is way too broad, it's more broad than just this. So can you talk a little bit more about how it relates to this?
Yes. Let's see. I'm trying to think if I have a slide on that already.
It's kind of getting, so that the hard part in my mind is actually learning the parameters, right?
Yeah, absolutely. So essentially, because of the because we can analytically integrate out those no parameters, we have like this perfect like collapsed Gibbs sampler, which you can see has this like probability of placing any bag given the placement of all the other bags. So then you can scan through the bags and sort of reassign them, reassign them, reassign them. And so it's actually pretty simple in this case because Dirichlet is conjugate to multimodal. It turns out to be pretty beautiful sampling. Actually converges really well. So we have these like 500 or more dimensional problems at SIBO, where we're using MCMC, and convergence is very difficult. And they're all discontinuities, and there's no complexity, and everything is strong covariance. But here, but here, even with tens of millions of data points, it converges like less than 10,000 iterations. And it depends on the distribution of your data. Okay, so that's kind of the math part. So how do we actually do it? We're good stewards of company time. We don't have to build everything from scratch, sir.
Sorry, before you move on to that stuff, did you look into at all how people might use like a distribution on their hyperparameters as well when you're experimenting with these different
Yes, there are good papers about like sampling over hyperparameters. We did not do that, but it can be done, and there are some great papers on it. Yeah, definitely, that's a great question. Yeah, we pick parameters, and it's for our problem at 1.0, and there's a range over which it's not very sensitive. You can really crank it up if you're smaller, then it's kind of silly. And if you just pick dumb parameters like the amount of smoothing is 0, and you have a bunch of 0 counts, your count vectors, those things are there's no margin for error. Other things? So we weren't going to implement it from scratch. We're like, there's this cool company, I don't know where they are, they're called in Boston, called Datenbox, and it's cool to use blog posts, it's open source stuff. We're doing exactly this. And so we're like, we will use it. No, I did not. So we put actually made some test data, like synthetically generated, known answer, 100,000 observations, shoved it in this Datenbox thing, and it summarily exploded. And so we couldn't do it. And the first reason it exploded, even though we put it on one of those like really beefy 150 gram EC2 instances, like couldn't even do one iteration, was because we had this vocabulary of like 10,000, 50,000 colors, and 100,000 data points. And it's using arrays like to store the count vectors. So you like have a sense vector, and you have this assumed red is in 0 and green is in 1 and blue is in the next one, and you sort of notice that almost all of the entries are 0, right? It's like hugely wasteful in terms of memory, and the amount of memory consumed is like of the size of the global color vocabulary, which in this case is big. So like we can be smarter than that. We can use sparse data structures. And so the easiest way to do that is to use a map, an associative array. Say like, pink is 1, and accrued, which I'm told is the color of linen, is 7. Because I couldn't figure out the last color belonging to let's see what happened. And that only takes memory proportional to the number of colors in a given actual bag. So way smaller, way more efficient, but it's in maps, so we couldn't use the data box code at all, and we had to rewrite it completely. But it did mean that instead of 2 gigs for our little test data set file, it was like 60 megabytes. We didn't have to share all the zeros. It ran in 2 gigs of RAM instead of, who knows, more than 150 because we couldn't even get to run. So that's like 333-fold reduction in I/O and like 70-fold reduction.
So there's implementation of this code in like in R or in Python or something like that?
Very, very slow for reasons we're about to talk about.
Oh, sorry?
It would be very, very slow for reasons we're about to talk about. So this was on Java, on the KVM. Okay, so it runs, but it takes, to do one of these gives samplings we're talking about, and you have to do one for every bag, every iteration. Yes, we call that a reseeding in a restaurant. It took 32.5 seconds in our sort of moderately sized test data set, 100,000 bags, and we wanted to do 10 million, right? So you've got 100,000 customers, and say you need 10,000 iterations for convergence. That's 1,000 CPU years on the sampler, so that's not going to work. Like, that's not the realm, even if we'd be like, oh, I'll just pay for a bunch of EC2 instances. Like, no way. It's not going to work. So, if you have any performance optimization, there's some in JVM, it's great tooling. So we use Visual VM, which is a profiler. You have to use Profiler 4. You can run it on your code. It actually rewrites all the methods on your code to insert timing operations around all the methods, and then it collects methods, right? So then it gives you this nice little chart of all your methods and how much time each one took. And interestingly, you have a method, it calls 5 methods, they call 5 methods, and subtracts the time of those transitive methods out. We call that the self-time. And you can aggregate all those across, you might have multiple places that call the same method. So it aggregates all those together and it normalizes the total execution time you get there. So you can run the profiler and find things that are a problem. So one is just running this code on all of the tables, like there's lots of tables. If you use sort of default initialization strategy, which is to put one customer at every table. So then you just start off with 100,000 tables. That's a lot of tables. At convert, that's this first sort of row. So as most tables, there's no like bias. I mean, you're not starting it off with any sort of pre-configuration that you have to climb back out of, but it's the slowest. Another strategy in the literature is to randomly assign people, random people to random tables to a total of log n tables, or alpha times log n tables. And this has many fewer tables, the fewest, right? I mean, log of 100,000, log n is like 16 or something. So a tiny number of tables. But it's kind of the most biased. Like you have to really climb out and put yourself in a local optima. So it's fast, but it's sort of biased. There's actually something really sophisticated we could do. This Downey 2007 paper I mentioned is makes this heuristic sort of all the input data, and at every step tries to place every item in every cluster, and it essentially does a beam search. So it keeps a heap of like the W best worlds, and so it doesn't just try to insert it into all the tables, it inserts into all the tables and all the worlds every iteration, and only keeps the top W worlds. And then it picks the best at the end. So it's kind of like a greedy search that's look back size to get you out of local optima. That was in MATLAB. We had to be implemented in Scala. Actually, had a bunch of bugs in the MATLAB from the paper. And it did work, but it actually ran slower than running the sampler on our big data set. Yes.
So each reseeding happens in W worlds at each step, and then that proves that over time, or?
Exactly. Yeah. So you have this like whole look back of the worlds. Which is a great idea, because you don't really care sometimes about sampling, you just want the best. You're assuming sampling is like a crappy optimizer, but that was his thesis too, which is totally true. It just doesn't work. What we actually ended up doing was to reassign in some number of tables K that was bigger than this log n, but smaller than one table per cluster, like 100 for 100,000, which has more tables but less bias. And we actually measured the bias in different sizes of tables. And that gave us a 5x. It's our first 5x speed up. The day. So I mentioned we're big into functional programming. So this whole code base is completely immutable and pretty and pristine. And At one point, we actually rewrote the whole thing to be immutable and like, oh, we can make it faster. And that turned out to be a mistake. We knew that's not what we do, because we should all know this, which is that most code that you performance optimize has like a single hot path through it. It's not like randomly distributed around. It's almost always a single hot path. It terminates in some like really slow interlude. That's like a classic archetype of performance, program performance. So if you look here, things that matter the most are really these pulling people out of clusters, putting them in other places, calculating their C's, and putting them back. That really takes a long time. So it turned out some of that is actually absurd.
When you say hot path, is that path takes a long time, or that path is executed a lot?
It's that it takes a long time. Because if it was executed a lot, but it was really fast, and we wouldn't care, it's that it makes up the majority of the total program execution time. So it's the product of those two things. So what we did is actually just change some of the code to be mutable, and this is actually kind of really dumb, but we used to have these clusters that have this sequence of members, which is immutable, and every time we want to change them, you have to sort of make a copy of that data structure, which is still efficient. Again, in these functional programming languages, those structural sharings make those really efficient. It wasn't enough efficient. So we actually ended up changing this to have members that are mutable variables that point back to the cluster that they belong to. So we could leave everything else, like the whole world, in green, immutable, and functional and pretty, and we just made this one little change that gave us another 5x speedup. And we did this in one other place that gave us another 5x speedup. So then if you look at that execution graph, that C function literally was called 1 trillion times. Literally a trillion times. So we're like, okay, can't do that. This is the C function from before. That's like one of these special functions that like magical integrals simplify to, which obviously you can expand into some numerical approximation, right, at the top, right. But man, like it's got logs and a bunch of divides which take forever, and more logs and square roots. Like, there's too many instructions, way too many instructions. So, and if you think logically what we're doing, we have all these sequence of numbers, and we're like mapping this function over it, right? Trillion executions. So the first thing, we're like, we have not very many different values that we're passing in this function. Because we're using counting. Counting is skewed low, right? And it counts up. And there aren't any counts at like 100,000, right? We don't have bags that have 100,000 M&Ms in them. So the sort of range of values we put in this function is pretty small. So you can make a cache, an evil, dirty, mutable cache, say, for simplicity. Say uses this cache getter else update. Like you would look up this function, started there, give it back to me, and that function call overhead is less than recomputing this terrible function. So that's like a big speed up. That's actually not the best we can do, because function calls are still really expensive. Like when you're calling it a trillion times, it's expensive, because it's still a trillion calls to this getter else function. So what we actually realized was, these functions only over doubles because we're adding this beta prior to our counts, right? So like, let's not do that. And for a given execution of the clustering, beta is fixed, like it's a constant, like with the configuration of the sampler. So we can pull that out and put it in the definition of log gamma, which means we have a function from int to int. Function int to int that's skewed low, that starts at 0, that has bounded domain values. Which means we can just pre-compute like the first 0 through 100,000 of log gamma plus beta and put it in an array, right? And we're just going to look it up. Like now the definition of log gamma is look up exactly that address in this array, no function call overhead, and then that function gets inline. So that's actually a 10x speed up. So then we get into even sillier things. So we have all these arrays and maps and stuff, right? But if you have a sequence of some generic sort of fancy Scala and generics and super abstraction of T, how's that laid out in memory? It's actually not a Python array, right? It's not this nice, pretty array of primitives. It's actually this array on the heap that has a bunch of pointers, and those point to objects that are like, could even be wrappers around values that have an actual value of an int. Not very efficient. So there is actually this crazy library in Scala called Ebox from Eric Osheim, who's super awesome. And it uses some crazy features, notably specialization. So specialization on the JVM lets you compile separate code paths for different types. So you compile a separate version of a method, like one version for ints and one version for doubles. And this annotation in Scala just auto-generates all those specialized bodies for you. But to do that, you also want to new up primitive arrays on the JVM, which are sort of the most performant data structures that exist on the JVM. And to do that, you need a way to new up instances of generic type, which you can't do in JVM, so we use class tags, implicit class tags from Scala. And then he re-implemented maps, everything in terms of arrays. That gave us another 5x speed up. No boxes. Maybe the most fun one is actually, we converted to those sparse vectors, right? So, we have pink is 1 and asparagus is 2. What is the fastest way to add two of those together? Seems like dumb and trivial, and you come up with those fun ways, like maybe I'll just iterate through one and like smash it into the other, or get the keys of one and the keys of the other, and combine those, or iterate over them. And you can, here's like 5 different ways to do that. And surprisingly, they have really different performance characteristics. Like what that version 2 is like 4 times slower than some of the other versions. And a lot of that is like, how can we avoid function calls? Because function calls get expensive and we do them trillions of times. And looking up something in a map that may not be there, and getting back to null, and then check if it's null, and you use get or else, and like make it 0, and you have to add 0 back in. Takes a lot of time. So we didn't do any of those. What we actually did is re-represent all of our sparse vectors as arrays of pairs of values. So all the odd numbered values are keys, and all the even numbered values are values that go with that key. And we kept them sorted. Sorted, like that's asymptotically more complex than having this unordered map. But the constant's really small because the number of colors in the bag is really small. So we keep everything sorted with these sorted pairs of values. So we have these 2 vectors A and B. The way to combine them is to tick through them in parallel, right? So this first, we tick to the first, we take whichever one is lower, and we emit it into the output array. So 3, 1, there's pink 1 is lower, emit it. And advance the left side. So now we have 15, 13, 13, it's that linen color. They're the same. So we emit the sum, and we advance both, right? And then 1 is argued to the end of the array, we have a value left, it's unique, we write it out, advance that side, now we have the sum.
Why are the keys sorted?
So we can do this trick of knowing how they line up. We can walk both arrays only once, we don't have to look for the keys, and we can do it all in one pass. Keeping them sorted means we can do it in one pass.
So when they have the same key in both of them.
Then we merge them, and otherwise we output them as simpletons. So that's actually a 10-fold speed up what we're doing.
So like in C++, you have ordered map and unordered map, right? So you could just begin with an ordered map and then you don't have to sort them.
But what are you going to do to look? You have to look up in the ordered map, which is a function call overhead.
Okay.
Which doesn't matter unless you can call it a trillion times. So
no, I mean, you could just compress them into arrays again, right? And then just...
And that's what this is, right? You're compressing them into arrays and they have to be sorted. Otherwise you can't do this. Or you incur function call overheads. So yeah, no function calls. So that's 10x. And sort of the last thing was, it's very easy to do parallel computations in Scala. We added parallelism in lots of places. And in fact, we made it slower in a number of places. So you really have to measure. And so we did lots of measuring. One place where it really doesn't matter is that C function in the posterior probability where we're adding a bag in and out of every cluster to see how well it matches and taking all those scores. That can easily be done in parallel and it's pretty expensive. So the overhead of parallelizing it is justified. And it's Scala, so we really just have to say .par, like on an array, and then everything automatically gets added to a fork join adaptive work stealing pool, and then pulled back from that. So it's literally this 4-character change. In the right place, got us this other 5x. So in total, that was 300,000-fold performance speed up on CPU, and then the sort of 68x on memory, 333x on I/O, and these sort of 7 Scala versions of this, which meant in the end that we could not make any compromises, no data subsetting, fully Bayesian, and do our sort of giant data set. That's it. And we're right on time. We can stay around afterwards, and I certainly can take any questions. I'm going to keep everyone else in time before I have to go home or something. But we are hiring. We're hiring lots of positions. Is it okay?
Oh, of course, yeah.
So Bayesian data scientists, obviously, are people who want to be Bayesian data scientists. We want to work on big models. I mean, we're like big data, but more big models than big data, because we're crop science driven. Anyone who wants to be part of the functional programming group, really passionate about that, and then fusing that with GIS and computational geometry with data science, and then also computer vision, remote sensing computer vision. So, and crowd modeling, junior developers, databases, systems. That's it. Any other questions? Sir.
So, as far as using Scala to do high performance computation, did you feel that let me ask the question slightly. Do you not feel that the abstraction that you get from Scala is really hiding the performance issues? Like, wouldn't you have had a much less miserable time if you wrote it in maybe Java or even C?
So, Java, no. If you don't do dumb things, then the Scala compiler optimizes almost everything into native Java performance. There's like a couple dumb things to do. C, sure. But I think what's interesting is the code base is, sort of for that whole project is larger. And there's really just that one hot path where we had to do like dork around and do silly things in.
But everything's just taking that and rewriting in JNI instead of insisting on keeping it inside Scala.
Yeah, we didn't think, because once we got to this level of performance, then it was okay for what we were doing. But I mean, it's definitely this trade-off of how much do you want the whole team to be able to interact with the code base, keep everything at a high level of abstraction, except for this like one hot path to the code, right? And what's actually interesting is we can use things like specialization to get this sort of native performance with unboxed arrays without having to, like that code server I showed, that's in the library, right? That actually rewrites all of your Scala code, and is totally type safe.
Right, so the problem from my experience in my own team where we actually do use Scala too, the problem with kind of having this snowflake of a routine within Scala is, yes, technically it's the language it's the same language that everybody else is using, but I better not let any of the junior engineers even smell that code, let alone touch it.
Sure.
So that's the trade-off. Like, yeah, you forced it to use Scala, but now you really need to have your super Scala ninja on a good day working on it, and only on a good day.
We tend to wind up in that situation a lot. I mean, not just from performance, but also even in really complex abstraction things, like forcing lots of things in the time system. So maybe part of that, I think, is also just education on the team, like bringing junior developers up to speed really quickly. I guess that's a trade-off. It's a trade-off. Like, you're totally right. Just trade-off that we've made.
And currently we are in the situation of having a big C++ code base that is being wrapped up with Scala, and there's a lot,
Oh yeah, C++
there are a lot
sucks. I mean, we're not debating.
We've got
I'm not
and
debating.
we're profiling the heck out of it in all these different ways. We've got profilers and there's debugging one side and transfer the other side.
So that's where my first question to you was, well, there's nothing out there that was already written by a published paper. The flip side of that, are you planning on publishing this code?
It's open source.
Okay, already. Oh,
yeah.
Awesome.
Yeah, could you give some kind of sense or measure of how much effort went into this speed up?
So the whole project, including like actually getting all of the data, making this, doing the actual data science, interpreting the results, making a web page like interactive for the results was like 8 weeks. So maybe this was a month of that for 2 people. It's actually not that much work after it works.
Sorry, could you give a sense of, I'm not sure if I missed it, but could you give a sense of what sort of hardware you use and the size of the data?
This was running on a single machine. Because the only thing that's easy to distribute is this like computing, going into all the tables. Actually, at this level then, I think the latency would be too high, getting a lot. If our problem were different, that might be different, but for the data we had, like MCMC is kind of fundamentally sequential, unless you do some really, really fancy stuff. So it's hard to do that in a distributed way. So we had to like use the little machine.
Will you be able to make the slides available? Can the slides be made available?
Yeah, I can slides available. If you email me, I'll send it.
Cool, thanks.
So do you think you can use GPUs for some of this too?
I think I saw a MCMC and GPU paper recently, but I don't know. I guess I don't know a ton about GPUs, but I guess we haven't usually used them because you have to have all these like lockstep operations that are perfect, and we tend to have all these crazy sprawling things. But maybe.
Not for 8 weeks.
Well, that depends on the programming model you're using. If you're using CUDA or something like that, that's very low level.
Yeah, but the thing with GPUs is you don't get the speed up immediately unless you think very carefully about your memory models of what you're shipping into the GPUs and all that stuff, which does not come for free, regardless of the language.
No, I agree, but with OpenMP4, that's the emerging model. You can have pragmas that just offload data to the GPUs, do the computation, and send the results back. So you don't have
it's
to
in the right form, the structure.
Yeah, you just need the right structure.
But I don't know.
Yeah, but that's the trick, right? It's like
structure.
getting the right structure really makes a big difference. And you won't get that 100x unless you really think it through. It's not like yeah, I'm just gonna recompile this or kind of take this code.
And there's someone who wants
Just
to
to
get it into
potentially change the subject slightly, but so I may have missed it, but the evidence example is awesome. Where does this fit into SIVO? And how are you fixing agriculture with your
So it doesn't fit in SIVO at all. It's only because we were SIVO and we were going to this DPMM talk here 2 months ago, and it was canceled. We were like, we love you. We do do a lot of Markov chain Monte Carlo over a much more complicated. Like I said, currently this 500 variable model that's really terrible, and execution of it is in C++ to evaluate the sort of instances. It takes 300 milliseconds for evaluation, and can't get analytic gradients because it's a computational function. But it's fun.
So, what kind of reality checks do you run on your output? I've done things using mixture models of T's, and there are different information criteria that are not necessarily very helpful. They're contradictory. So you're actually getting a distribution of clusters, and then if someone comes up to you and says, well, so how many kinds of bags are they? Are you going to just tell them a distribution, or are you going to have some argument for at least the plausibility of your distribution?
The web UI that we had for the specific data we're doing in this project that I can't talk about, but it just basically took the map estimate, right? The maximum a posteriori estimate of the world. But there are interesting measures, and I sort of alluded to that when we talk about them. But because every cluster is defined by this Dirichlet Compound multinomial, you can say like, how well does every member fit, like really with this cluster? Like, how good is every cluster? What's the probability this person really goes in a different, like, and we actually showed a lot of those on this UI. So I do think that's really valuable and helpful.
I mean, do you do it? I mean, the simplest thing would be to, I mean, which you probably have done is, you know, simulating the data, and then you know how you generate.
And that's what we did for software testing, was like generate 100,000 bags with this 10,000 vocabulary size, with sort of exponentially distributed counts in them, and an exponential size of every group, and then have the weights like, you know, distributed within each of those vectors, and then try to recover that data back out with synthetic, you know, known synthetically. The problem is when you synthetically generate it, sometimes like you generate an observation that really is equally likely to go into, but it's still good to make sure it stuff's working.
Have you tried approximate inference or like some MCMC better than like give sampling?
Probably could be fine, but it's like approximation. You just make it go faster. But yes, that is the thing.
And MCMCs other than the GIPS, there are some newer MCMC methods like Hamiltonian.
I know. That's what I was lamenting, not having the analytic gradients or even being able to do auto-diff, which is what Stan does, which is Hamiltonian. And for some things, like I think the Venture is actually more able to do DPMMs. I think there's a hack in the Stan manual of how to kind of do some of this with Stan, but because it doesn't have first class support for discrete variables, in Hamiltonian Monte Carlo, it's hard. If you can analytically integrate them out, I think is how they get rid of it. But you can always do that.
There's also one Hammer MC and EMC, like other packages that does Hamilton MC.
With the parameters alpha and beta, how do you set them? Do you have an idea, or do you have to do a lot of trial and error to get the proper values?
Beta, in my experience, is the hard one to set. It's relatively insensitive changes in alpha, but beta is this like smoothing over the multinomial. It's not smoothing, it's really a prior probability that interpretation happens to over the colors in the vocabulary in the bag. That's kind of dependent on how many observations you have. So it's more tricky to set beta. So we did some scans to see like where is it, you know, what's it over that range, and then that's the hard one.
All right, so I think that's a wrap. Really glad you guys stopped by this nice and new couple of get to talk. Ryan and Marisa, that was a fantastic talk, and love it. Thanks for giving us so many questions. So, only thing I have to say is actually an interview that's coming next week, September 14th. And I think that's over at CSC. Forget what it is on, but check out the other side, and we'll see you guys there again. So, again, thanks to Ryan and Marisa for putting this talk together. Thank you very much.